Today we want to perform a computer simulation lab, the purpose of which is to determine the value of Coulomb's constant. The problem, always phrased in the form of a question, will be what is the value, the experimental value, of Coulomb's constant. And of course we're going to have three sets of variables. One manipulated variable, one responding variable, and then we have, well, what amounts to almost an infinite number of control variables. But we'll put a little asterisk beside that because I don't expect you to list 5,000 control variables. You guys know the deal from before. I expect you to list the really important one or ones in this. Usually there's one or two really important control variables that you've got to keep the same. Hopefully that becomes obvious to you as we work through the procedure. The procedure is going to be rather straightforward. When you open up Google Classroom, you're going to see a link under the assignment. And that link is going to take you to an applet, a Java applet. That's going to look something like this when you open it up. You see at the top of the page, there's two charges listed. Notice they give you the symbol for a charge as a capital Q. We usually make it a lowercase q, but that doesn't really matter, right? Notice as well that you have the charge given to you in microcoulombs. That's okay to list the data as microcoulombs, but when you go to do a calculation with it, you need to make sure you convert that to coulombs. When you open it up, you're going to see your default charges as 1 microcoulomb and 1 microcoulomb. It doesn't really matter, but I'm going to suggest to you that you change one of the charges to some other value. Maybe 5 microcoulombs, maybe 6, maybe whatever. If you want to change both of them, go ahead. It doesn't really matter. Now down below you see these two charges a certain distance apart. Be careful that this 1 centimeter that's given to you here is not the distance separating these two charges. That's just the scale on this grid, 1 centimeter per block. So what you see here is a distance, well, it looks like almost 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, almost 10. Actually lists the exact value of the distance down below, 9.9 centimeters in this case. And it also tells you the value of the force. F1, the force on the first charge, is 4.59, and go figure the force on the second charge is the same value. Equal and opposite, right? Object A applies a force on B, B will apply an equal and opposite force on A. So here's what I want you to do. Once you open the app, you want to set your charges here. Okay, 1 and 1. It says make them different from one another, but it doesn't really matter. Okay, I'm just suggesting you do that. 1 and 1, 1 and 5, whatever the case may be. Then you want to record those values. Record the values of those charges. Then record the value of the separation distance, and that's given to you just as a number. So just write it down. And then finally record the value of the force that acts between the two charges, which could be either F1 or F2. Then, listen carefully, then what I want you to do is change this value from 0.0990 or whatever it happens to be, change that value. You're going to do that not by typing it in here, but you're going to do that by literally clicking on one of these charges and dragging it to the right or to the left. I don't care whether you go bigger or smaller or bigger, 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 and then smaller. It doesn't make any difference what order you do it in, as long as you get at least 10 different separation distances. And of course, as you change that separation distance, you're going to measure how the force changes because of that separation distance. So this distance will change, but this force will also change as a result of you changing the distance. Of course, if we're going to change this and this is going to change because of it, then these two things have to remain the same, right? Do it at least 10 times, get at least 10 different values for R and 10 corresponding values for F. When you do that, you should get a data table that looks something like this. Charge 1, charge 2 in microcoulombs, or you can change it to coulombs if you want right away. Eventually, you're going to have to do that anyways. And then 10 different separation distances and 10 different corresponding electric forces. What do you think you're going to do with that? Put it in a graph. Yeah, you plot a graph of force versus separation distance. I'm saying F versus R, but of course you'll use the words force and separation distance. You're going to title it as well. When you do that, you're going to get a graph that looks like, remember doing this yesterday? It's going to look like this. Good. Exactly. It's going to look like this. What you're going to do is insert a trend line but you're not going to bother inserting an equation because the equation isn't going to be very helpful to us right now. Just insert a trend line that matches. I'll give you a hint. Don't make it linear because that's not linear. Make it fit. Because this is a computer simulation, your data should be really, really good. And if your trend line doesn't fit really, really well, then you've probably made a mistake with which trend line you're choosing. Just choose again. Once we have this graph plotted and we recognize that, oh, the shape of this graph gives me an f is related to 1 over r squared relationship, then we want to decide to straighten it out so that we can deal with it, so that we can analyze this graph. Because we recognize that it's an f versus 1 over r squared relationship, then we're going to create a new table that is not r and f, but rather 1 over r squared and f. Right, I'm saying this is, f is related to 1 over r squared, so let's plot a new graph of f versus 1 over r squared. So if r was 10, then r squared would be 100, and 1 over r squared would be 1 over 100, or 0.01. So it goes from 10 for the value of r to 0.01 for the value of 1 over r squared. You can have Google Sheets do all those calculations for you. All you got to do is set a formula in there once, and it should copy the formula down, and it should do the calculations for you. So plot this graph, f versus 1 over r squared. What do you think the shape of this graph should be? Yeah? Yeah. F versus r gave you this graph. F versus 1 over r squared gives you a straight line, because that is the relationship in the equation. Now, you guys more or less know what to do with this. We've done this once before with our first activity that we did. Figure out the significance of the slope. Well, we know it's a straight line, y equals mx plus b. That's why I straightened it, right? I don't want to deal with this as an equation. This is way more difficult to deal with as an equation. Okay, this is easier. It's a straight line. And y equals mx plus b always applies to the straight line graph. My y-axis is force. My m is the slope. My x-axis is 1 over r squared. In b, the y-intercept is going to be 0, or it should be fairly close to 0. And now, of course, you've got to get an equation that matches up with that has both f and r squared in there. Which equation do you think I'm going to use?
The right one.
This one isn't rocket science, right? Which equation has both f and r squared in there? Coulomb's law, yeah. So we're going to say f is equal to k q1 q2 over r squared. You guys remember what to do next? Start crossing things off, because it appears in both. Because it appears in both. What am I left with? Slope is equal to this. What was the problem in this, by the way, again? You remember? Define Coulomb's constant. So Coulomb's constant is simply going to be the slope divided by q1 times q2. Get the value. Right? You get the value of the slope from Google Sheets, divided by the product of the charges. Just make sure you convert those charges to coulombs as opposed to microcoulombs. Otherwise, you're going to get a value that's way off by a factor of 10 to the 12, actually. What's your conclusion going to be? What was your problem? What's the value of Coulomb's constant? So your conclusion is the value of Coulomb's constant is blank newtons times meters squared per Coulomb squared. And then some people in the last class were calculating a percent difference. That's okay, but that's not what that's not what we were trying to find, right? We weren't trying to verify it, we were trying to find it. If we're trying to verify it, well, then we should compare it to the accepted value of 8.99, right? But if you're trying to find it, we're pretending we don't know what its value is in the first place. So if you find it to be 8.72, that's fine. Say the value is 8.72. This is known because, and then just give me a brief explanation. Basically, it amounts to Coulomb's constant is equal to the slope of a graph of the f versus 1 over r squared graph is equal to Coulomb's constant times Q1 times Q2. So you manipulated that, I'll get this right eventually. You manipulated that equation in order to find the value of Coulomb's constant. Done.